from the homework on page 296. We are going to look at number 51 and number 53. Number 51 says find domain of a function f, and it gives us f is equal to square root of x divided by some stuff. And we have 2x squared minus 3x minus 5. Okay. So I can see that there are two places where this thing could go wrong. First off, if this were just this function, there's no denominator or anything like that. If it just said f of x is that x, or 2x squared minus 3x minus 5, I could say, well, we have no problems. I could plug in any number there. That's perfectly fine. In this case, though, that thing is in the denominator. And I know that as of right now, we really only have two restrictions, right? One is that denominators cannot be 0, right? We can't divide by 0. The other thing is we cannot put negative numbers into roots. So we'll deal with these one at a time. And I notice, okay, one of the major problems we might have is if this thing is equal to 0. And so what I'm going to do is basically see where that happens. In other words, for what values of x is this true? When does that denominator actually equal to 0? So what do we do when we have something like this? Are you frozen? Am I frozen? Can you hear me?
You cut out for like.
Cut out?
Yeah, we're good. We're good. We're good.
Okay, we're good. So you're following, right? Like we have a denominator. We need to see where that guy is equal to 0.
Mm-hmm.
And now we are, what do we do now in order to get to this point? How do we
Factor it out?
Factor it out, right? So I know what this thing's going to look like. We're going to have something like this. What goes in the first place?
A 2x.
2x, I like that. And then what's in the other first place?
Just an x.
Just an x, right? Because 2x times x gives me the 2x squared. So what goes in the last place? What are my possibilities here?
Your possibilities are oh.
5 factors into what?
3 and 2.
Wait a second. 5 equals 3 times 2?
It doesn't factor. 5 and 1, I guess.
5 and 1. Those are the only possibilities, right? 5 is prime, which is nice. So which one do you want to put where? I don't know right now. So
I guess put the 1 first and then the 5 second.
And then the 5 second. Okay, so let's try that. So we go outer gives us a what? What's 5 times 2x?
10x.
And then the inner gives me what?
1x.
Is there any way I could add or subtract these guys to and from each other to give me a negative 3x?
No.
No. So let's flip them. We did 1 and 5. Let's try 5 and 1. What's my outer?
2x.
And my inner is what?
5x.
How can I combine these guys to give me a negative 3x?
A +2 and a -5.
There we go. And so this looks good. I'm going to put a 5 here and a 1 here. The only thing that remains is to figure out what signs go where. Who gets the negative and who gets the positive?
2x -5 and x +1.
There we go. Now what I'm going to do is just double check that and make sure that this is indeed equal to that. First, give me 2x squared. Good. outer is +2, inner is -5. 2 minus 5 is -3. X is, yes, -5 times +1 is -5, and so we're good. And so this gives me two possibilities for X. This means this will be true when this thing is 0. So X plus 1 is 0 when X equals what?
1 minus 1.
Minus 1. And what about the other one? Don't have to do it in our heads. We can always just do this. 2x minus 5 equals 0. And then we'll just solve for X.
So plus 5.
Uh-huh.
And then divide by 2.
So
5 over 2.
5 halves. And what I'm going to do is I'm just going to double check that. When X is equal to 5 halves, and I could see that, yeah, if I plug that in there, right, the 2 times the 5 halves minus 5, the 2's are going to cancel. We'll have a 5 minus 5 equals 0. Plug that into there, and that entire thing will be 0. And so, yeah, there we go. So what we found is that the denominator will equal 0 whenever this is equal to that, or whenever X is equal to 5 halves, or when X is equal to -1. So that means that we cannot have these in my domain. Because if they are in my domain, we have division by 0, which we cannot. So we have to pull them out of the domain. Okay. Now, what about this? What restrictions do we have on what we put into a square root?
It can't be a negative number, right?
Right. And so how do I write that? This is what? Whatever goes in there is, how do I write that as an inequality?
Wouldn't you just write X?
Well, yeah. But as an inequality, I'm trying to be a little bit more general here, because in general, if this were, say, 2x minus 1, I would be saying, it's 2x minus 1 that has to fit some inequality. What inequality do we have? Say that again.
X cannot equal 0. I mean, negative, blah, blah, blah. X is greater than or equal to 0.
There we go. There we go. And I like to think about it this way, because we don't want to get in the habit of, X has to be greater than or equal to 0. Because that's not the case here, right? It's whatever goes into here has to be greater than or equal to 0. So I would do this type of thing right there if that were my problem. I would say, that entire thing has to be greater than or equal to 0. And then I could work from there. So that's kind of what I was saying. That's why I like to do this fill in the blank thing. It's whatever goes into the square root has to be bigger than or equal to 0. So X has to be bigger than or equal to 0. Okay, so now we have two restrictions here. On one hand, X has to be greater than or equal to 0, and X cannot equal 5 halves, and it cannot equal -1. So what I'm going to do is think about just the interval first. And in order to do that, I like to draw my number line with infinity up here and negative infinity down here. And this, since X has to be bigger than or equal to 0, I'm going to go ahead and put my 0 here. And since X has to be bigger than or equal to it, I'm going to make an interval this way, just like that, and say, okay, everything that's bigger. And so these are all allowable inputs. And I can see that this is true, right? If I take anything over here, if I take a 3, for instance, plug in a 3, no problems there. Okay, that looks good. I actually can plug in 0 too. 0 is in that interval. And if I plug in a 0 there, no problems. Good to go. Now we have two other restrictions, right? X cannot equal -1. So we have to have a hole here at -1. But that's outside of the interval. So we don't even actually have to worry about that, because since we know we can only put in these numbers anyway, this guy doesn't even come into play. He's not going to factor into our analysis, because we're only looking at these numbers anyway. But there is a number in here that we cannot have. And what number is that?
5 halves.
5 halves. So we're going to have a hole here. 5 halves. We're going to pull out 5 halves, leaving me the open intervals, or well, leaving the open endpoints here, right there and there. Now, how would I write that as an interval or as a union of intervals?
So you'd have, you would add, okay, add domain.
Yeah, well, what? Yeah, the domain of F is
equal to hard bracket 0, comma 5 halves.
Yep.
Soft bracket.
Yep.
Union.
Yep.
Soft bracket 5 halves.
Yep.
Comma infinity.
No, what we're saying here, soft bracket, there you go. Now, what we're saying here, what this means is that the domain of F, in other words, the allowable input values that we could plug into this function, the things that we could let equal are in this interval. We cannot have 5 halves because if we tried to put in 5 halves, guess what? This thing will give me a 0. It's going to blow up. We cannot do that, so we had to pull it out. The other restriction was that whatever went into here had to be positive or 0. So we include 0. And we have all the other numbers. Any number you choose in here, like for instance, 1 is in this interval, this little sub interval here. And if you were to plug it in, you'd be perfectly fine because you would have, let's see, f of 1 is the square root of 1 over 2 times 1 squared is 1, minus 3 times 1 is 1, minus 5. Okay, you have square root of 1 is 1. 2 minus 3 minus 5, that's the same as 2 minus 8, which is 1 over negative 6. Perfectly fine, no problems there, right? Ditto with all the other numbers that are in this interval, you'll get something that makes sense. But if you go outside of that interval, like down to -1, you'll be plugging a -1 in here, and we can't do that yet. We're not going to consider those types of functions, so it's not in our domain. Ditto, we can't, well, -1 would also make this blow up, but sorry. Can't plug in a -2, can't plug in a -5, can't plug in 5 halves. That's why we had to pull it out because that would give you division by 0, et cetera, et cetera. Does that make sense?
Yes.
Okay, so that's the idea with all of these domain and range things. We're only working with domain. We're finding the domain of a function. Basically, we're asking what values either makes this thing blow up. In other words, what values would I plug in that gives me a division by 0? And then saying we can't have those. And now we have a new restriction, which is that whatever goes into a square root or a 4th root or a 6th root or any even root cannot be negative. So we're dealing with these two things and kind of blending them together any way we can. So with number 53, it says, find the domain of F where F is equal to the square root of x plus 1 all together over x plus absolute value of x. Yikes. Okay, that one's ugly. Let's wait for the ugly thing first, right? Thinking about domain, what do we have to have for this? This gives me a restriction, and what is it with the square root?
X is greater than or equal to 0, or x plus 1 is greater than or equal to 0.
There you go, right? It's whatever goes into the square root has to be greater than or equal to 0. So that means that x has to be what?
-1, right?
Greater than or equal to -1. And so I'm going to go ahead and get a visual here because I love drawing pictures. It helps me with all this. And I'm going to say, okay, -1 lives right here. And it has to be bigger than or equal to that. So it has to be on this side. So to draw that, I'm going to have a hard bracket just like last time. And it's all of these numbers here. So if I take any number in this interval, I have no problems with the top. So that's good. The only thing that remains is dealing with this bottom one. And that's really ugly. But what equation am I going to use? Just kind of thinking back to last time. How did I deal with this? What do I have to do with this? Pretend for a second that this was exactly what we did last time. Pretend for a second that this were something over 2x plus 1. You would say this can't be something, and what would you have?
That can't be 0.
Right. You would say this cannot be 0. And so in this case, you would say what cannot be 0?
2x plus 1 cannot equal 0.
2x plus 1 can't be 0. Okay. So just by analogy, what do we do here?
X plus the absolute value of x cannot equal 0.
There you go. So this is what we have to do here. We're going to say this. And the way I did it before is I just said, yeah, I know that what I'm getting at is that we don't want it to be equal, but let's kind of figure out where it is equal, and that will give me the problem points here. So what do we do? Yeah, it's a little ugly. I don't really know where to go with this either, but maybe if we just take one of those to the other side of the equal sign, maybe we'll see something that will help us. I don't know, but let's just try it. How about let's subtract x from both sides.
Okay.
Subtracting off this x gives me absolute value of x is equal to negative x. Now, this is kind of ugly here. I'm not really getting a feel for this. But let's think about what the absolute value of x is. The absolute value of x is always positive, right? Like if you plug in, like let's just graph it, actually. That might help. Here's x, here's y, and we're going to graph y equals the absolute value of x. So when x is positive, the absolute value of x is just x, right? You plug in a positive 2, and you get out a positive 2. You plug in a positive 3, you get out a positive 3. It's just this guy right here. Goes up like that. It's just the line, basically y equals x. But when it's negative, right, I plug in a negative 1. What's the absolute value of negative 1?
1.
Positive 1. What's the absolute value of negative 2?
Is 2.
Positive 2. And so really this thing kind of looks like this, right? Plug in a negative 2, I get out a positive 2. Plug in a positive 2, I get out a positive 2. Okay? I'm looking at this and thinking about it. It's like, okay. So first off, what happens if I plug in a positive 1 into this equation right here? Let's just see. If I plug in a positive 1 for x, I get the absolute value of positive 1 equals negative positive 1. Is that true? Is 1 equal to negative 1?
No.
No. Okay. So we don't have to worry about that. Like and in fact, any positive number I plug in is not going to make this happen. So we don't need to worry about the positive numbers. Let's just do one more just to be sure here. If I plug in a positive 2, is that ever equal to negative positive 2? Well, no, because we have negative, this is always going to be positive. So we just have positive 2. Is that ever equal to negative 2? No, we don't have any problems with that either. So it looks like I'm never going to run into a problem when I'm plugging in positive numbers. Let's try a negative number. Let's try negative 1. What happens when I plug in -1? Let's see. Absolute value of -1 is
1.
And -1 is
1.
oh. Ooh. So when I plug in -1, this is equal to 0, and we cannot have that. Right? Just like, let's just go back to the very beginning of this right here. Right? What we said is if I plug in a -1 here, just plugging it in, will that give me a 0? So we have -1 plus absolute value of -1 is a +1. It does give me 0. Uh-oh, that's no good. We can't have that. So we can't have -1. -1, we have to pull out -1. Ditto, we have to do the same with -2, right? If I plug in a -2 here, I'll have -2 plus the absolute value of -2. Well, -2 is just -2. The absolute value of -2 is a +2. -2 plus +2 is indeed equal to 0, which will make my denominator blow up. So I cannot have that. It looks like all negative numbers that I use are going to do that. Let's just to really drive the point home, let's just take a general negative number. Let's call it -a. And if I plugged him in right there, I would have -a plus absolute value of -a. Gives me -a plus absolute value of a negative is a positive. That does equal 0. So it looks like we cannot have any negative numbers. Can't put in any negatives. Why? Because if we do, this thing right here will equal 0, and then we'll have a 0 in the denominator. It will be bad. But there's one thing that we didn't talk about. We talked about strictly negative numbers. We talked about strictly positive numbers. What's the only thing left that we need to check? Look at the picture. We did everything on the right-hand side. We did everything on the left-hand side. What's sitting right there smack in the middle that we didn't check?
0.
0. Usually, honestly, if we're doing this on my own, it would be the first thing I check. I always just 0 is an easy one to check. It usually makes your whatever you're plugging it into, it usually makes that expression a lot easier. So, but I'm saving this. I saved it here in this case. But let's just see what happens. If I plug in a 0, I get a 0 plus the absolute value of 0. What's the absolute value of 0?
0.
0. What's 0 plus 0?
0.
0. Can't have it. So we can't put in any negatives or 0. Okay. So now we have 2 restrictions. Okay. What we just found from this part here, right, from this work that we did, we found that anytime we plug in 0 or anything to the left, we get a division by 0, which we cannot have. So what I'm going to do, actually what you're going to do is tell me how to write that as an interval. If we can't put in 0 or anything negative, what interval am I left over with?
X is greater than 0.
Right, and what does that look like as a picture?
So soft bracket.
Yep. Soft bracket. Where? At what number?
0.
At 0, right? Here's 0. And soft bracket facing which way? Yeah, that sounds weird, huh?
Towards you.
Yeah, I get, yeah, opening towards me, coming to eat me, right? Yeah, so this way. And we can take everything that's bigger, right? Everything that's bigger is fine. We don't have any problems with that. Okay, but we cannot include 0. Okay, so and now I haven't really drawn this very well. What I should have done is kind of kept the scale the same. So if that's -1, and then I guess 0 would be here. And so here's 0. And now we need to find the interval that makes both of these true. If we're going to pull a number out of one of these guys, well, clearly if I'm over here, it's fine. They're both in there. This number is good. This number is good. But if I choose something like this, like -1/2, -1/2 is in this interval. And it'll be fine in there. I could plug it in here. There's no problems. If x is -1/2 plus 1, I'll have, well, -1/2 plus 1 is just +1/2. That's perfectly fine. I could plug in a positive number into here. But down here, I'll have a problem, right? I'd have -1/2 plus the absolute value of -1/2, which is -1/2 plus 1/2, which is 0, which makes this guy blow up. So they're not both satisfied. So when it's called intersection. I'm finding out where these two intervals intersect, where they overlap. And what would that be? Where they're both true.
Okay. So wouldn't you have a hard bracket on -1?
Well, okay.
No, never mind.
Yeah, because remember, we're trying to figure out where both of these are true. So anything down here is not going to work. So what's left over?
Well, isn't it just the one we had in the middle?
Yeah. Yeah, it is. In this case, it is, right? And so it's not really a trick question. It's just kind of simple in this case. But the idea is the same. Like if these were more, if let's say the top interval gave you something like this, like we're only taking numbers from -1, including -1, up to 2, and they both had to be true, then when we intersect them together, we would have to take numbers from 0 up to 2, right? And that is how we would intersect those and say, yeah, anything in this interval will be in this interval, and it will also satisfy this interval. But in this case, like you said, it's pretty simple. Like we don't have to worry about that crazy stuff. It is just that middle interval. So how do I write that in interval notation? The domain of F is what?
Soft bracket.
Yep.
0 and then infinity. Soft bracket.
Bracket. There we go. And just making sure that this works. Plug in 0 or anything strictly bigger than 0. I'll have, well, obviously a positive number, right? And that's perfectly fine. And there's no problems with the top right here. I won't have any negative numbers going into a square root, so we're good. Also, I could see if I plugged in the 0, I would have division by 0, but I'm not doing that because we're not including 0. And so any positive number is a positive plus a positive. Both numbers will be bigger than 0, so I won't be dividing by 0. So I feel good about this answer right here. And that is the answer to number 53.
Okay.
And we could just write, I'm not sure what it says in the back of the book, but it could be something like that. X is strictly bigger than 0, which means the same thing here. This will, and you kind of see, like if you had something like this, if you're working with your intervals like this, some of this. Let's say we had done all this work and we ended up with these two intervals, and we had to see where they were true, like where they were both true, and you ended up with answers like this. And I said, okay, well then where are they both true? That's kind of hard to see. I don't know about you, but when I'm looking at that right there and you say, okay, so where are both of those, where is X true for both of those? I have a really hard time with that. But if I drew it out like this, and this is why I'm really stressing interval notation, is that it becomes pretty easy to see. You just draw these two lines and say, well, where are they both true? Well, where they overlap, right? Like we can only take values in here, not including this guy. We can only take values in here, not including this guy. So where they're both true is where they both intersect, where they both overlap. And it's going to look like this from 0 up to 2 when I make those guys intersect.
Got you.
So that's why it's one of the reasons I'm really stressing doing the interval notation, right? It's it makes life a lot easier than just doing this. Well, this would be true, like say the set of X where both of these are satisfied. It doesn't really help you, you know. So, okay, that is that. Any other questions from homework or anything like that?
No.
Okay, now let's move on. So, one thing I'm going to address this really quick. I was going to spend more time on this, but I think it would be better to just wait until later. But I do want to briefly talk about this. When we have to address negatives inside of roots. Like that's can be very difficult stuff, right? Like when we have a square root of, say, if I just wrote the square root of -2, we'd know, wait a second, you can't do that. You can't have a negative number inside a square root. Okay. But if I had something like this, -2 squared, say, well, wait a second. That's perfectly fine because -2, what is -2 squared?
The 4.
Say it again. I couldn't hear you over Peter.
-2 squared is the same as just 2 squared, right?
Yes, exactly. It's +4, right? Or in other words, 2 squared, right? And so okay. Moving along here. Let's stick with this train of thought. Okay, so if I have, say, a positive number, and we know it's positive, it's a numeral, right? It's a given numeral. I don't need to worry about it because I can look at it and see, hey, that's a positive number. I don't need to worry about negatives. Okay, cool. But I had something like this. In fact, let's make this a little bit easier. Instead of 2, let's make this a +4. +4 right there. And x squared. We'd say, well, I know that the square root of 4 is what?
2.
And the square root of x squared is what?
X.
You think so. And you'd be like, okay, so I'm done, right? Well, no, because what if x itself was a negative number? What if x was, say, -3? Well, then that doesn't really work because you can't, because then what you've just said, so let's say what I'm getting at here is, let's say you're doing some work on a problem and this, you have a bunch of different steps that you're working on. Somewhere along the line, you have this. And so you say, oh, this right here is just 2x, okay? And so then you do some work later and you find, oh, x equals -3. Ah, I have my answer. It is equal to -6. And you'd be absolutely wrong because what you've just said here is that the square root of something is a negative number. No, it's not. It's not. We're not doing that, right? So just like what we said before, though, is when you have a negative number and you square it, it's the same thing as the positive number here. And so then what comes out? What's the square root of 2 squared?
2.
2, right? I mean, this was part of your homework, right? Like any number here, and you have, say, 2 to the k, it's equal to just 2, unless that original number was a negative number. And so what we have to do here is say, well, we have no problem with the 4. We could see that the 4 itself is a positive number. But the x, like I said earlier, the x might be a negative number. And so we have to say absolute value of that guy. Okay, and that is the key here, because then when we go to plug this guy back in, we say, then we're doing, like I said, we're doing some work and we end up at this intermediate step. We do some other work and find out, x is equal to -3. Then when I plug him in, I end up with that. And then we can say, that's actually 2 times +3, and it does give me 6. And that makes sense that you could have, you took the square root of something and got a positive number. So long story short, whenever we have an even powered root, and we're simplifying this, which is what we're going to be working on a lot today, we have to use these absolute value signs. Because again, we don't know. X might be a negative number, right? It might be the case that what you were originally working with was 4 times -3 squared, but you didn't know that it was a negative number. So then when you go to pull it out or whatever, it has to be absolute value. So does that make sense? Mm-hmm. So I think, you know, you've had a bunch of those in your homework from last time, and this is going to continue to come back and bite you in the butt. And we have to keep that in mind, right? But here's the thing. In your homework tonight and for a while, all of the numbers that you have, not the variables, not the unknowns, but all of the pure numbers that you see inside your radical are going to be positive numbers. And when that's the case, we don't need to worry about it. We only need to worry about it when it's a variable and we don't know whether or not that variable is positive or negative. And then we have to say, it's the absolute value we have to deal with right here. Okay.
Your video went out.
Great. Let's see how long it will be like that. Okay, so today. So did all that make sense? Do you feeling good about that?
Yeah.
Okay, give me just a second. And actually, what I want to do later on when we start talking about complex numbers, we're going to come back to this idea of having negatives in the radicals. And I'm going to give you I want to say algorithm, more like a flow chart for how to deal with this. But I've looked ahead at the next few sections, and every one of these guys that you're going to see, the numbers out in front are all positive numbers. And so with the numbers themselves, we don't have to worry about how to deal with negatives, really. Okay. You have to remember that when you have an even numbered root and you pull something out of an even numbered root, it had better be an absolute value. Otherwise, what you just said doesn't make sense. Mm-hmm. So you're going to encounter that. Okay. So we're working with roots or radicals. I will use those two terms interchangeably. And what we want to do is, we're going to have to manipulate them a lot. We will want to multiply these guys together. We will want to simplify these expressions that show up under a radical. And in order to do that, we are going to talk about a rule. And your book just states it without giving you any kind of proof or any kind of reason why it should be true. So what I'm going to do is talk about why it's true. And we're going to start with an example. Everything we're about to do right now, we are looking for a rule involving radicals. And in particular, when you multiply two radicals together, what do you get? But what I want to do is start with a specific example of something. And then we're just going to follow some reasoning and play with some stuff. And then, of course, the specific example, when you're plugging in a couple numbers, like actual numbers, we're going to be using 2 and 3. Of course, that's not going to apply across the board. So we're going to make this a bit more general and then introduce variables and convince ourselves that, yep, the same thing's going to be true when you just use any old variable. And that's going to lead us to a formula, or in your book, it's given as a theorem. And that is going to help us enormously in the future. But I want to justify that formula. So everything that we're doing right now is to arrive at a formula involving radicals. Okay, are you ready? You ready to begin?
Sure.
Okay, so what we're going to do is square stuff. We're going to take an input and square it. We kind of know what squared looks like. Okay, so for instance, if I take 2 and I square it, what do I get?
A 4.
I get 4. But what I'm going to do, I'm going to write it as 2 squared first. Okay? We'll get to 4 in a second. But right now, just by definition, 2 squared means you take 2 and you square it, which, yes, we know is 2 times 2, which, yes, we know is 4, but we'll get it. So what about 3? What do I get when I take 3 and square it?
You get a 9 or 3 squared.
9. And we'll just write it as 3 squared. Just by definition of what we're doing is what we're doing. We're taking inputs, we're squaring them. The thing that comes out is whatever that original number was, and then squared. Okay, now I want an actual number. What is 2 times 3? 6. Okay, so if I take a 6 and square it, I get what?
36.
Yep, and I'm going to write that as 6 squared. Okay. Now here's a cool thing to notice. It turns out that, okay, this one was obvious. I took 2 times 3 and I got 6, but I'm going to think about that number here, 6, as 2 times 3, which is 6. But the idea is I'm taking 2 numbers, multiplying them together, and getting a new number. And I'm using parentheses here to symbolize, like, that's my new number, 6. Okay, here's another cool thing. What happens when I take this number times this number? What's 2 squared times 3 squared?
What was that? 6 squared. Okay, so 2 squared. Wait, what? Sorry.
What's 2 squared times 3 squared?
6 squared.
It is 6 squared. Interesting. Multiply those 2 and you get that one. You know, and then we have our outputs here, and it turns out, this isn't necessarily always going to be the case, but it turns out to be the case that when you multiply those 2 together, you get that one. There seems to be some kind of relationship here. And you can kind of see why this has to be the case if you look at 6 as 2 times 3 squared. Because let's look at this whole equation that we have. We have 2 squared times 3 squared. 2 squared is 2 times 2. 3 squared is 3 times 3. The cool thing is I could do multiplication in any order that I want to do. I could do 2 times 3 times 2 times 3, right? I just switched these guys around here. Instead of saying 2, 2, 3, 3, I said 2, 3, 2, 3. Then I can regroup this way and say, well, it's the same as doing the 2 times the 3 times the 2 times the 3, or in other words, something times itself is just that thing squared. And so 2 times 3 and 2 times 3, that's what goes in here. We take 2 times 3 squared. And that's kind of what we were saying earlier, right? Like that is 6. And yes, that indeed is 6 squared. So we have this nifty little relationship here that this times this gives you this, therefore, this times this gives you that right there. Okay, okay. Now, what I want to do here, I just really want to convince myself of this. Let's think of the actual numbers here, because we're all this squared and stuff like that. Like, yes, it makes perfect sense, but let's just really convince ourselves that this is true by doing this. What's 2 squared?
4.
4. What's 3 squared?
9.
And what is 6 squared?
36.
Okay, okay. So I'm just going to double check this, right? We know that 2 times 3 is 6. That one's obvious. And is it the case that 4 times 9 equals, what is 4 times 9?
36. Oh, right.
Huh?
All right. I forgot about this.
Yeah, it's a nifty little thing. 1, 2, 3, 4. That is 36. Yeah, so okay, this is all consistent, right? And we could see that it looks like it has to be this way, right? Like everything is kind of, and this is why it has to be that way, because we could rearrange these guys to give you, oh, that thing right there. 6 is 2 times 3. Okay, that's cool. But we haven't proven anything. This might just be an artifact because these happen to be prime numbers. Maybe it doesn't work if you're using composite numbers. Maybe if I used 4 and 8, something might go awry. I don't know. So let's just knock this out and do it in general here. So in general, instead of, I started by taking 2 numbers, 2 and 3. Let's give them new names. Let's call them U and V. I took a number U, I took a number V, and then I multiplied them together to get a new number. What's U times V? I'm being a jerk here. U times V, we're going to do the same kind of thing that we did here. We're going to say, well, you took 2 numbers and multiplied them together. We're going to think about it as one number. In this case, it's just you, whatever you get when you do U times V, right? So we took 2, multiplied by 3, we get 6. Of course, 6 is just 2 times 3, yeah. And so U times V, those are distinct numbers, but when you multiply them together, you get a new number. And I'm just going to write it in parentheses so that we have it in our minds that that's a new number that you got when you multiplied these things together. Okay. Then what was the next thing we did? We threw U into squared. And what is U squared?
U squared.
U squared. There you go. I should say, what is U multiplied by itself? How can we write that? It's U squared. So what is V multiplied by itself?
V squared.
V squared. Now, what is UV multiplied by itself?
UV squared.
UV squared. There you go. Whatever that number happens to be. Now let's just keep in mind that this is the parallel we're doing, right? We took a number, squared it, and it came out to be whatever that number was squared. We took 3, we squared it, and we got 3 squared. Same thing here. U is U squared. V goes to V squared. U times V, we actually had a name for it. It turned out to be 6, but then we took it and we squared it. That's all we're doing here. We've taken U and V, multiplied them together, got a new number that we're writing in these parentheses, and then we're going to take that number and square it. Okay, cool. Now here's the thing. we could show that the same kind of thing is true. First off, right, we noticed, get some more room here. And this is obvious. U times V is whatever you get when you go U times V. That's the obvious thing that we started off with. But now let's just kind of prove to ourselves that the same thing is going to happen over here, that when I take that number times that number, I do indeed get that number. And so that's what we did before, right? We took 2 squared times 3 squared. So let's do that over here. That times that is U squared times V squared. And I'm going to follow the same line of reasoning up here. I'm going to say, well, U squared is just U times U. V squared is just V times V. I could rearrange these orders, and I get U times V times U times V, right? I mean, do you believe that? Do you believe that we could do multiplication in either order and we get the same thing?
Yes.
Yeah, I believe it. Okay, that sounds good. And well, since we could do multiplication in any order, it's also associative, right? Like we could do this first. We could say, well, that's the same thing as U times V times U times V. In other words, whatever we get when we multiply U times V is just a number, right? Just like here, we had 6 times 6, and it turned out to be 6 squared, but we're just writing it as that number times that number times that number. But that's what it means to have whatever this is, UV, whatever that number happens to be, finally squared. And so the same thing is true over here. That times that is that guy right there. That's what we just proved. U squared times V squared is the same thing as UV squared. Okay. Right now we have nothing involving radicals. And what we want is a formula involving radicals. So what I could do, and I'm going to start by doing this on the top one to see how I might get a radical out of all of this. Remember how we defined the square root, right? We talked about it as being the inverse of this operation, right? Like when you take something and square it, you get a number. Like you take 2 and square it, you get 4. To do the opposite is what we mean by square root. We say, you take 4, take the square root, and it brings you back to 2. In other words, 2 is the square root of 4. In fact, the square root of 4 is just a fancy way of writing 2. Yeah? Do you believe that right there?
Yeah.
Yeah, right? That's what it means, right? We have the number, yes, we have 2 squared, but then we gave it an actual name. We said, well, it's not just 2 squared. It has a name. It's 4. And so when we take 4, whatever that number is, and we pull it back, you get 2. In other words, 2 is the square root of 4. And that's a little equal sign. Instead of writing it sideways, I'm writing it up and down to say 2 is equal to the square root of 4. 3 is equal to what?
9. The square root of 9.
Square root of 9. 6 is equal to the square root of what?
36.
36. And hey, look at this. We know that 2 times 3 is equal to 6, right? So let's just think about this. We have 2 times 3 is equal to 6, but we know that 2 is the same thing as the square root of 4. We know that 3 is the same thing as the square root of 9, and we know that 6 is the same thing as the square root of 36. Oh, that's interesting. So before we're not ready to make a conclusion yet, but I noticed that there's this relationship, right? That we have the square root of something times the square root of something equals the square root of something else. And it's clearly true. The square root of 4 is 2. Square root of 9 is 2. Square root of 36 is 6. And so when you multiply those together, you get that. That's pretty cool. Okay, moving along here. Let's do the same kind of thing. Let's use the same kind of reasoning that we did here to get our square roots, which is the thing we're trying to prove something about square roots. So we need square roots to show up here. But look at what I did. I didn't call this the square root of 2 squared. I didn't call this the square root of 3 squared. I gave them new names, right? So let's give these things new names. And oh, I don't know. Let's let u squared equal maybe x. And let's let v squared equal, oh, I don't know, y. Something like that. Let's do that right there. So v squared is equal to y. We're giving it a new name. U squared is equal to x. We gave it a new name. Real quick, let's just see what this has to be then. We know that u squared times v squared has to equal uv squared, but we also know that u squared is the same thing as x. We also know that v squared, we've renamed him and we've called him y. So x times y has to equal uv squared. In other words, whatever, and this, I'm just kind of restating this, right? I'm just saying 4 times 9 is 36. U squared times v squared is uv squared, but now we're giving it new names. So x times y is that thing right there. We're going to give it a new name though, xy. Okay. Now, same way we did before, right? We had all of our outputs here, and then we just said, well, by definition, you could pull them back with the square root. And we gave all of our outputs new names, so everything looks nice and unique. That's what we've done here. Now we have the output is x, the output is y, and the output of that guy is xy, whatever that is. So now, finally, how do I write u as a square root? U is the square root of what?
Sorry, I'm writing everything down.
Okay, no problem. And it's just, we're just reasoning by analogy here, right? Like we could really just look up at the original picture and say, well, that goes there, and that guy's got to go there.
Oh, your camera went out.
Okay. There we go. Okay.
Oh boy.
Oh, yeah, this is frustrating. Okay.
Okay. Yeah.
There we go. Okay. So in our original one, we renamed 2 squared to 4 and then said that 2 is the same thing as the square root of 4. So here we've renamed that guy as x. And so then u is equal to
the square root of x.
Square root of x, right? And really, I'm really just using an analogy here saying we took a number and squared it. Well, that has a new name, you know, it has a new symbol. So let's give this one a new name, a new symbol. You take u and square it, it'll give you a new number. And so it's x. So by definition, when you undo that, that's the square root of x. The same way that the square root of 4 is 2, the square root of 9 is 3. So then v is equal to the square root of what?
The square root of y.
Mm-hmm. And uv is equal to the square root of what?
xy.
xy, whatever we get when we, the thing we get when we multiply those things together. And it's exactly the same thing as we did here, right? Like 36 was, yeah, okay. So now, finally, we finally arrived at the thing that we wanted. And it's been a long journey, but here we go. Finally, we could say, wait a second, u is the same thing as the square root of x. Cool. V is the same thing as the square root of y. Cool. uv is the same thing as the square root of xy. And now we have, in general, we could say, this is how this works. And indeed, it does work, right? Like the square, what this says, right? I'm just going to plug these in here and say, okay, then it should be the case that the square root of 4 times the square root of 9 is equal to the square root of 4 times 9. And let's see, so that means the square root of 4 times the square root of 9 is equal to, what's 4 times 9? Oh yeah, 36. Square root of 4 is 2. Square root of 9 is 3. Square root of 36 is 6. 2 times 3 is 6. This is what this means right here. And we can see why it has to be true. And it came from what square root means, and the fact that we just took these two numbers, multiplied them together to get a new number. We had to do some finagling and stuff, but rewriting these as square roots gave us a very, very helpful formula right here. And this is going to be what we use over and over and over again. Okay, so this is, your book just states it and says theorem, and then it tells you this. And in fact, it tells you something a little bit different. It says that at any root, the kth root of x times the kth root of y is equal to the kth root of xy. And I didn't bother with that because I said squaring's easy, but you could imagine that if instead of using 2 here, I used k instead, that we said we're going to raise something to the kth power, well, then these would just change into k's. And then when we pull them back, by definition, they would be the kth roots. But the argument would be the same. It would just look really ugly when you're trying to do this in general and say, what's 2 to the k and 3 to the k? Well, you'd have 2k times and 3k times, and then you'd rearrange, and it just looks ugly. But do you believe that it'll work when you use any power here?
Yes.
Yeah, right. And so that's the idea. By the exact same argument we just used, we could prove the same thing for a general root. And indeed, it is the case that for any value of k, this works. Any value of k? Any value? Yeah, I think any value of k should work. Okay, so except 0. Well, we'll get into that soon. All right, so why do we care? Who cares? Like, really, when you're looking at this, you're like, all right, big deal. This is really useful to actually go both ways. Like, now that we have this, and when you look at a formula like this, you think, okay, I see what's going to happen. You're going to give me something, the root of something times the root of something, and tell me how to get that. And indeed, yeah, we're going to do that. There's going to be plenty of that. For instance, let's take the cube root of 7 times the cube root of 3. What is it? I'll give you a hint. It's the cube root of something.
7 times 3.
7 times 3, which is what?
21.
21. Cube root of 21. Yep. And you're going to have some homework problems like that. It's going to tell you to do that. You're also going to have some homework problems like this. You're going to have the square root of x plus y times the square root of x minus y. I'm going to go ahead and erase this. This is going to be we need to have this in our brains for the rest of our lives. So basically, the product of roots is a root of the product. Okay, so I'm going to erase this. All right. Now, the square root of something times the square root of something is the square root of what?
X plus y times x minus y.
Yes, and whenever we do that, we have to make parentheses our best friends. They are our best friends and we must treat them as such. So whenever you see something in a root, go ahead and think about it in your head as it has parentheses around it. Hey, buddy. And so when we multiply an expression under a root times an expression under a root, we think about them as in parentheses. Hey, buddy. We think about them as that. And what does that equal? What is x plus y times x minus y?
X squared. Hi, Peter. Sorry, whoa. Minus xy plus xy is not, and then minus y.
Minus what?
Minus y squared.
There you go. Okay, this is our old friend, right? The difference of squares breaks down like that, or conversely, it breaks down like that. Now, do not make the mistake of saying, oh, well, then that equals x minus y, because that's not true. I've seen so many people make this mistake. This is not a perfect square. This does not work. And let's just prove that to ourselves. Let's suppose that it were equal, which it's not. This is not equal to this. Let me show you why that's true. Let's suppose that x equals 3 and that y equals 2. Over here, we would have 3 minus 2. Over here, we would have the square root of 3 squared minus 2 squared. What's 3 squared?
9.
What's 2 squared?
4.
What's 9 minus 4?
5.
The square root of 5, if this were true, which it's not, if this were true, this would say that the square root of 5 is equal to 3 minus 2, which is 1. I guarantee you the square root of 5 is not equal to 1. So you got to be really careful with this, really careful that when you have something like this, you think, oh yeah, the square root of something squared, it just pops right out, right? No, that is not equal, not equal ever. It will never, ever be equal unless one of them is equal to 0.
Right.
Okay. So that is part of what you're going to be doing, right? You're going to say, okay, yeah, there's that. That's x squared minus y squared, and there you go. And so there's some utility in that, right? Like, whatever, like, we're not going to get into it, but this will be useful to be able to go in this direction. What's even more useful is to go in the opposite direction. That is, you start with something that is a product and break it apart. For instance, $12 is equal to what times what?
6, no.
Oh, yeah.
6 times 2.
6 times 2. Okay. So we could write that as the square root of 6 times the square root of 2, right there, right? Because by our theorem, like we know that you multiply two things together under a radical, it gives you the same thing as doing that right there. There's another way we could have written this. What else is 12 equal to? Something times something else?
3 times 4.
3 times 4. Okay, and so that comes out to the square root of 4 times the square root of 3. What's the square root of 4?
2.
2 root 3. So you're going to be doing this a lot. And this is probably the most important application of this theorem right here. This is what you're going to be using all the time. And it does, believe it or not, make your life way easier when you could do this.
Okay.
Okay, so now here's the thing. Your book does it like this section. this is how it tells you to break stuff down, like almost as though you're supposed to know that, well, get into this. We could have written this way. We could have said this is the same thing as 2 squared times 3. And then broken this up as the square root of something squared times the square root of a prime number. And then we see, yeah, 2 with the square root and it cancels and good stuff like that. I prefer, when doing these, to break everything down like this. I'll show you why in just a second. So moving on. That guy. So let's say we have the cube root of 24. Now, what I like to do is just, I'm going to go ahead and just factor this guy completely. 24 equals what times what?
12 times 2.
Okay, 2 times 12. And 12 equals what times what?
4 times 3.
4 times 3, or how about 2 times 6?
Okay.
So I'm trying to factor completely. So I'm going to break it down completely. And this is kind of the way I like to do it. I'm going to get rid of all my evens first because it's nice and systematic to do it that way. 6 is what times what?
3 times 2. Or 2 times 3, yes.
Yeah, right. Okay. And so now I could see that we could rewrite 24 as, this is just the way I do it. You could do it any way you want. This is just, I don't care how you choose to break down 24. If you've done it right, we'll end up at the same answer, that it's 2, 2, 2. So I have 3 2s times 3 right there. And I recommend that when you're doing these problems, you just break it down into prime factors written as exponents, because that's going to make your life a lot easier. And I'm going to rewrite this then as 2 to the 3rd times 3, which I could rewrite as the cube root of 2 to the 3 times the cube root of 3. What is the cube root of 2 to the 3? 4. It's fork, buddy.
Wait, it's not 4.
No. Peter is saying the word fork. And it sounds like another
Oh.
word. I have to really enunciate when he starts saying another word that sounds like fork.
But it's
trying
not.
to teach him it's a hard R. Otherwise, it sounds, yeah. And so,
Okay.
So, yeah, what is the cube root of something cubed?
Oh boy.
We did this one earlier. This is the whole point.
It's just going to be 2, isn't it?
Exactly. And this is why it's nice to do this, because then I could just see, oh yeah, 2 to the 3rd, the 3s, and that's the idea, right? You took a number and you cubed it, and then you uncubed it. It just comes back to whatever that number is right there. And then that's times the cube root of 3. That can't be factored down any more than that, right? So let's do this now. Now this is going to look like hell at first. It's going to look really bad at first. And I'm not going to recommend that you actually do it this way, but I want to show you why. What I'm going to recommend that you do, I'm going to show you why it's true first. So I'm looking at this and I have a cube root. So I'm thinking, well, what's nice is whenever I have some number raised to the 3rd, I get to pull one of those numbers out. And so if I had, let's say we started with some big number and we did all of our factoring out and it turned out to be, let's say, 2 to the 4th times, let's say, 3 to the 5th times 7 squared. Okay? What this is, and this is the part where I'm going to say, you don't need to do this. This is a bit too much work, although to be honest, this is how I did it for a long time because I just don't trust myself with numbers. I wanted to see what this looks like. 2 to the 4th means 1, 2, 3, 4 2's all multiplied by each other. 3 to the 5th means 5 3's all multiplied by each other. Okay. 7 squared means 2 7s. Finally. Okay. And now I'm thinking, okay, well, I'm taking a cube root. So if I group these things by 3's, that's going to help me out a lot. As a matter of fact, I could group this into one group of 3's right there. I could group this into a group of 3's right there. And now let's see what we end up with. We have the cube root of 2 to the 3rd, or in other words, 3 2's. So 2 to the 3rd with 1 2 left over. This would be 3 to the 3rd with how many 3's left over?
2.
2 of them. So I'm going to write that as 3 squared. And can I group any 7's together? Can I group 3 7's together?
No.
No, we're stuck with 7 squared. Now here's the cool thing. And this is, I do not do it this way. But I want to do it this way so we can really just prove that we could do this final step that I'm looking for. So we could split this up, right? With our nice theorem here is that when you have two things multiplied by each other, you could split it up into those things. So I'm going to split this guy off right here and say, that's the cube root of 2 cubed times the cube root of, and then I have another product, right? So I could break down that product into 2 times this and say, okay, well, there's a 2 left over. Another product, so I'm going to break him down into the cube root of 3 cubed times that, which is the cube root of 3 squared times, again, well, I mean, I could do that, but he's not going to break down at all. Again, I don't recommend doing this step right here, but here's the thing to notice. The cube root of something cubed is whatever that thing is. So that guy comes out to just be a plain old 2. Cube root of something cubed is whatever that is, which comes out to just be a plain old 3. Cube root of something squared, nothing's going to happen there. The cube root of something squared, can't pull anything out, can't really simplify that. So I'm just going to keep them together, combine these guys back together. 3 squared, 7 squared. Now I could rearrange the order. Again, I don't recommend doing it this way. We're going to do this a lot quicker. But I could rearrange this as 2 times 3, and then 3 third root of 3 squared times 7 squared. Finally, I could bring these guys back together because nothing can factor out of them. And I get 2 times 3 is 6 times the cube root of 2 times 3 squared times 7 squared. But what I could do, instead of going through all these steps, this is why it works, right? This is why we're going to end up at this. But we're not going to go through, well, we're probably not going to write it out like this. We definitely want to write it out like this. But all of these steps right here are really unnecessary because I could see what's going to happen, right? Like when I look at this right here, I could see, oh, 1 2 is going to come out in the end. 1 3 is going to come out. And then everything else that's in there that's not a perfect cube is going to have to remain in there. So from this point right here, I would go ahead and say, and I'll do this in another color here. From right here, I would just say, okay, this comes out as 1 2. This comes out as 1, 3. And everything else, I can't pull anybody else out. And so they're gonna have to stay inside that radical, and we're left with a 2 times a 3 squared times a 7 squared. And if I wanted to, yes, 2 times 3 I know is 6, and so I could write it like that. And there we are. That's how we ended up right there. So that's the name of the game today. Oh, jeez. She dropped out.
Just now?
Yeah, a second ago. Hey.
Hello?
Hey, what was the last thing you heard?
I honestly don't remember what the last thing I heard. I texted you. I said that my computer, it just like died without warning. Usually they give you a warning, but it didn't give me a warning, and it just.
Nice.
Sorry.
Great. Hey, no, it's not, whatever. Oh boy. Do you remember doing this right here?
Yes.
Do you remember going, how far down here did we get? How many steps?
I think to the
Did we get to this final, did we get to where we got the answer here?
No.
Okay. Did we get to where we split this up into individual dudes here?
Yes.
Okay. So that's what we're doing, right? And again, we're not going to do it that way. That is not the way we're going to do this. But this is why this works, is that this times this breaks up into 2 roots. And then since that's a product, that breaks up into 2 roots. Since that's a product, it breaks up into 2 roots. And finally, that's a product, so it breaks into 2 roots. And the idea was, if we do this smartly, right? If we group these by 3s, then we could say, oh, it's a cube root of something to the 3rd. Well, I could just pull that out by itself as one of those things, right? And ditto with the 3rd, 3 to the 3rd, the cube root of that comes out as 1, 3. We have a 2 left over, and these guys are left over. And so I said, well, nothing's coming out of these guys. I go ahead and group them together. Then I said I could redo the order of multiplication to get all my pure numbers out front. Bringing this guy over and saying, well, these roots are not going to simplify anymore. And so I could bring them all back together like this. And we end up with 2 times 3 is 6 times the cube root of all of the stuff that wasn't a multiple of 3, basically. We don't have enough to cancel anybody out. And so this is as simplified as it can possibly get right there. But then I said, like, we're not gonna do this unless you want to. And honestly, I did this for a long time where I just wrote out every single number because I didn't trust myself. And I was like, okay, you know what? I'm just gonna write out every number. 2 to the 4th is 4 2s. 3 to the 5th is 5 3s. And then I could just look at that and say, oh, you have 3 of them, you could pull out 1 of them. You have 3 of them, you could pull out 1 of them. And then everything that's left, right? Everything that is not a group of 3 has to stay inside. And so you're left with 1 2, 2 3s, and 2 7s. And indeed, yeah, that's what we end up with right here. But I said that the way that you'll probably do this is you break it. You could just look right here and say, well, 2 to the 4th, that's the same thing as 2 to the 3rd times 2. So you have 1 left over, and just rewrite it like that. 3 to the 5th is 3 to the 3rd, again, grouping by 3s, because I know that I could pull out 1 group of 3s. 3 to the 3rd right there, and then with 2 of them left over. 7 squared is, we don't have enough to even play with. So I could go from here to here and say, there's my group of 2s, pull them out and write it right there. There's my group of 3s, so I get to pull out 1 of them and write it right there. Everybody else has to stay inside, and then we could just finally clean it up here. And I mean, if we wanted to, we could multiply all this together and get a nice number, but we're done. That's the idea. And I just wanted to go through this because this is the reason why it works. But as I do these types of problems, I'm grouping by this number, whatever number root we're taking, grouping them into that, and then pulling stuff out.
Mm-hmm.
Does that make sense?
Yeah.
Okay, so let's do an example from the homework here. Oh, it's also a cube root. Yeah, I should have used a different root. Okay, so actually, well, this is an example from the problem set. This is an even one, so you're not going to see it. Okay, so the cube root of 108 times m to the 5th. So let's factor 108. 108 is equal to what? We don't have to go by twos. Like we could do this really any way you want to factor 108. I do believe it's 12 times something. I think. I could be wrong. Yeah, it is 12 times something.
9.
9 times 12. 9 is what?
3 times 3.
Okay. And 12 is what?
3 times 2 times 2.
Hey, nice. I like that. So I'm going to go ahead and factor him out that way and say, all right, we're taking the cube root of, we have 3 3s. Oh, nice. That's going to be nice. And then 2 2s, so times 2 squared. Now, how can we write m in terms of 3s? How many m's do I have, and how can I regroup them?
We have 5 m's, so to the 3rd times m to the 2nd.
So say it again.
Well, if you want a group of 3s, right, then m cubed and then m squared.
There we go. And honestly, this is what goes through my head. I have to, I can't just play games with numbers. Like I can't think, oh, then 3 and 5 and so 2 left over. I have to see it like this. Like I don't write it out every time, but I imagine, okay, I have 5 of them, group 3 of them together to give me that. What's left over? 5 minus 3 is 2. Yeah, right there. Okay. So now that we're here, what can I pull out? I already know that there's going to be 2 things that we could pull out. What can we pull? What's the first one we can pull out?
I'm sorry, I was just interrupted.
Okay, no problem. Okay, so what's one that we could pull out?
M.
We could pull out an m because that guy is m cubed. You're taking the cube root of m cubed, and so he comes out as 1m. What's another cube we could pull out?
3.
1, 3, right? We have 1, 3 there that we can pull out, leaving me a 2 squared and an m squared.
Mm-hmm.
Which, I mean, if we want, we could write as we could write as 3m, 4, m squared right there. And I mean, either one of those is fine. If you want to keep it factored, that's cool too. But that's the idea. Now, here's the hard part. Let's say we had done this. Let's say it was the same thing, except instead of m to the 5th, we had m to the 13th. There's no wrong way to do this. Well, there's a bunch of wrong ways to do it, but how do we want to take care of that? M to the 13th. if we were to group that by threes, right? How many groups of threes would we have? And so on and so forth, right? Because that's the idea. We have 13 M's total. And so one of these would be M to the third. And I'm just going to kind of group these as M to the thirds. How many of them do I need and what will be left over?
You need 4 of them and then you'll have 1 left over.
I think so. Because yeah, 3 times 4, right? If we really want to get tricky, we could do it like this. Aha. Whoa. Oh man. Yikes. But then, oh man, M to the 4th to the 3rd. Oh, yikes. That's really ugly. At this point, I would not want to play around with this. While this is true, this is going to make your head spin. But for right now, I would recommend, because I don't think you have anything with the 13th power, but that's the idea, right? Is like 13 is 12 plus 1. And so 12 times 3, it'll give you 4 groups of M cubes. And you don't have to write it out, but I mean, you want to get the right answer. I like to see it. You could do this any way you want. So now, what can we pull out? Let's just go one at a time. Can I pull anything out with the 3s?
Yeah.
How many 3s can I pull out?
Just the 3 cube, right?
1, 3.
Yeah.
Okay. What about 2s? Can I pull out any 2s?
No.
Okay, so he stays put. What about the M's? How many M's can I pull out?
4.
A total of 4 of them, right? Because each one of those is 1. And so I pull out 1 M and that guy's gone. I pull out another M, that guy's gone. I pull out another M, that guy's gone. I pull out one more M and make that a 4, and that guy's gone. Okay, this is a bit like, you could just remember like, oh yeah, that's 12. 12 is a multiple of 3 and blah, 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 blah. However you want to do this, you're going to get plenty of practice in your homework with this type of stuff. But that's the idea behind it. This is why we could do that, because for every one group of something to the 3rd power, with this being a 3, you could pull out one of them. There's 2 more things we need to talk about before we do your homework. The first group of stuff from 1 to 13, it says multiply. And it's going to give you stuff like this. It's going to say square root of 5, square root of 7, multiply. And so you just go, oh, well, that's just 5 times 7. That's just 35. Yeah, 35. Okay, boom, done. The second group of stuff is like what we just did. You'll be given something like the square root of 175 y to the 6th. I'm just going to do this quickly. I think 175 is $1.75. That means I could divide it by 25, because 25 is like a quarter. And I know if I have 4, 5, 6, 7 quarters, I have $1.75. So this should be 7 times 25. Okay. So 7 times 25. Y to the 6th. Ooh. Okay, we'll get there. But now I'm thinking, wait, this is a square root, right? And so I'm looking to group things into groups of 2s or into squares. How can I rewrite 25 as a square? 25 is what squared?
5.
Squared. And now that y to the 6th. Honestly, what I like to do, it's 6. It's not that much. It's going to take me a second to do that. I could just write those out. And now I could just go, well, here's one group of 2. Here's 2 groups of 2. Here's 3 groups of 2. So it looks like I could pull out not 1, not 2, but 3 y's total. And we could just say, okay, 1, 5 comes out of there. 1, 2, 3 y's come out of there. And I'm left with, oh, looks like just a 7. And I would be wrong. What was the very first thing we talked about with even roots? We didn't know whether or not this thing is a positive or a negative number. And so if it happens to be a negative number, this might end up being a negative number. And so we'd have to say the absolute value of the thing that we don't know right there. You following with that? Mm-hmm. That's the trick with all of these. The numbers, like I said earlier, all of the pure numbers that you get out front, they're all positive. So we don't need to worry about them. 175 is 7 times 5 times 5. Those are all positive numbers. Don't worry about it. These variables, we don't know whether they're positive or negative or not. So in the end, if you're pulling them out of an even root, and a square root is an even root, we have to talk about the absolute value. Especially in this case, because it's cubed. If it happened to be, we get to the end with something like this. If it happened to be y squared, we wouldn't have to worry about an absolute value because something squared is always positive.
Right.
So feel free to leave it like that if it comes out, if an even power comes out of an even root, feel fine to leave it like that. Or if you just want to be 100% certain, you just do that anyway. I don't care. Either way, we're good. But when it's an odd power coming out of an even root, you gotta be careful, because if that number in the beginning happened to be a negative number, you can't just plug it in because you'd get a negative number and yikes. Okay, so that's that. The final thing is it's going to tell you to multiply and simplify by factoring. And so here's a very simple example. I guess we'll do a square root. It says the square root of 5 times the square root of 10. It says to multiply and simplify by factoring. And so multiply, it says take 5 times 10. If you want, you could do this. You could say, okay, well, 5 times 10 is 50. And then 50 is 2 times 25, which is 2 times 5 times 5. And since we're doing a square root, every group of 2, we get to pull out 1 and you get 5 square root of 2. That's cool. That's a perfectly good way of doing it if you want to do it. If you want to do it that way. Or you could say, wait a second, why multiply this and then factor it out when it's already kind of factored out? Like I could just say, well, wait a second. Look at this. That's just 5 times 5 times 2. Oh, 2 5s. One of them gets to come out. And there you go. Right? So your book went through every example it showed was something like this, where it did the actual multiplication and then broke it into something that was a perfect square or a perfect cube, if you're talking about a cube root, which this is not, but whatever. I don't like that. Just break it down and then count up how many of these things you have. And if it's a square root, every 2 of them, you get to pull out 1, etc. So that's the last type of question you're going to have. You will have, then you're just plugging something into there. That's easy. And one critical thinking question. So that's it. Any questions? Excuse me.
Not that I can think of at the moment.
Okay. Yeah, so I recommend just factoring stuff down.
Okay.
way easier. So multiplying, simplifying by factoring, and then you'll have multiply and simplify. Don't do it the hard way. Do it the easy way. It's already half factored. Yeah. So okay. Okay. I think that should be it. Having all kinds of technical problems today, and yesterday, and the last time, and I think the time before that too.
Yeah, the Wi-Fi here is really unfortunate.
Let's see. Okay, so this is. Why did you do this? Whoever had this book before me decided to white out all of the page numbers. Thank you, buddy. So that's 296, 297, 298. 299.
Why would they do that?
Buddy, just 1 second. We'll see Kayla in just a second. So homework, chapter 7, section 2. Chapter 7, section 2. Numbers 1 through 39.